Okay, good morning, guys. Today we're doing 13.3, day 2. Should be kind of a short lesson here, but pay close attention. We'll move right along. So this is the rest of the week. Tomorrow we're going to do 13.4. Why is this not working? Here we go. Wednesday, 13.5, day 1 and day 2. And this Friday, again, you will have another formative that you'll be expected to take on Friday. Maybe we'll open it Thursday afternoon again and have you take care of it at that rate. So what I'd like you to do here is, this is not in your note packet, as it says right there, okay? Not in your note packet. Just do this on a scratch piece of paper here. We have the square root of x minus 3 under the root plus 4. Find the domain, the range, the y-intercept, and the x-intercept. Little review from last Thursday. Okay, we're back, and yes, those last two questions were kind of mean for you here, but what is the domain? The domain, just remember, to find the domain of one of these functions here. Okay, now just remember, in order to find the domain, all you're really concerned with is what is underneath the square root function. So we're going to take x minus 3, and we need to make sure that what comes out of that, when I put those together right there, that's always going to be non-negative or greater than or equal to 0. So I just write myself an inequality, solve that inequality, and bada bing, bada boom, there is my domain. To find the range, well, all I'm doing is I'm saying, well, I know y is talking about my range, and I take that domain value there, and I put it into the function, and I evaluate the function, and this is going to be 0 plus 4. So when I put the beginning domain value of 3 in there, I know my range is going to start at 4. And then all I'm going to do is I'm going to pick another number in here. Any number greater than 3, say I put a 4 in there, well, that's going to give me the square root of 4 minus 3 plus 4. Well, that actually gives you the square root of 1 plus 4, which is going to give you 1 plus 4, which is 5. And 5, this is where you would see your 5, is greater than 4. Now the y-intercept, okay, don't get all wigged out on this one. Remember, we want to find out what is y when we put 0 in for x. Well, that's going to give me the square root of negative 3 plus 4. This, imaginary, so I'm never going to hit the y-axis. The x-intercept, well, we want to say what makes my function 0, x minus 3 plus 4. Well, what can I put in for x? Take 3 away, take the square root of it, add 4, and get 0. Well, that's impossible because this is always going to output positive numbers, right? So, yeah, there's not going to be one of those. I know, it was mean and nasty. So, there you go. Well, let's move on. Composition functions were useful to help combine functions, but it turns out they are also useful with inverses as well. We already know that these two functions right here are inverses from each other, okay? And we're going to find the following composite functions. So what we want to do is we want to take f, and we want to plug g, which is the square root of x plus 9, into it. Well, what does that give us? Well, that's taking the x from my f function, and I'm going to square that and subtract 9. Well, remember, squaring a square root gets rid of the square root. And plus 9 minus 9, that gives me just an x. Well, what happens if I plug f into g? Well, f is x squared minus 9. So what I'm going to do is I'm going to take my square root here, where my x is, I'm going to put an x squared minus 9, and then we're going to add 9 to that. Well, notice there's really no use for these parentheses in here anymore because there's a big grouping symbol underneath that whole thing. So I'm just going to get rid of that. And I'm going to say the 9's go away. Well, that gives me the square root of x squared. And the square root of x squared, hey, that's just x. Right? So what do you notice here? What appears to be the relationship between inverses and composition functions, composite functions? Well, the composition of a function and its inverse equals x. What does that mean? That means f of g of x equals x, and g of f of x equals x, okay? Now notice we're not looking at numbers numerically like we did on Thursday, okay? We are actually plugging in a function and simplifying a function to find out. If both of these composition functions, if you plug one into the g into f and f into g, and you simplify them, and you get just at equaling x and only x, they are inverse functions of each other. A couple examples we're going to run here. Are the following functions inverses? Okay, notice they are both in function form, so I know they are functions. Are they inverse functions of each other? Well, I need to find what is f of g of x to find that out. So I'm going to take my f function here, and I'm going to plug my g into it, which means f is negative 8 plus, now I got to put my 2x plus 8 in there, and that all gets divided by 2. Well, what do you notice here? Well, I notice I got negative 8 plus 2x plus 8. I see those 8's fall out, and I'm left with a 2x over 2, and those are going to reduce. So that is going to equal just x, f of g of x equals x. Woohoo! Now that's not enough. We got to make sure g of f of x also equals x. So we're going to take g, and we're going to plug f into it. And when we do that, well, that's 2 times negative 8 plus x over 2. And then I got to take a plus 8. Well, remember, multiplication is the same. Well, just so I could write this out, this is really 2 times negative 8 plus x over 2, isn't it? Plus 8. And remember, that 2 will get rid of because that's going to reduce. So I can really see that happening back here. But then I have negative 8 plus x plus 8. Negative 8 and 8. Hey, that one just equals x as well. So g of f of x also equals just x. So yes, inverse functions. Okay? Yes, they are inverse functions because both of these are true. One of them can't be true. They both have to be true for this. This is an algebraic justification whether two functions are inverse functions of each other. Well, how about these next two in number 2? Well, we got to find f of g of x. So that means we're going to take f and we are going to plug g into it. Well, that's taking f here, which is my negative 4x plus 9. That is getting plugged in. I'm subtracting 4, and I'm dividing by negative 9. Well, what do I see? Well, my like terms here are my positive 9 and my negative 4. So I get negative 4x plus 5 over 9. Is there anything I can do to reduce that? Okay. Then there's not anything to reduce that. And this is unequal to x. Therefore, not inverses, I should say. They are not inverses of each other because it didn't equal just x. As you can see, that's a lot more than x. Why don't you give the next two a try here, and I will be back with the answers. Okay, we're back here at number 3. So what we need to do are the following inverses. Well, we need to find what is f of g of x, or you can find g of f of x first too. It doesn't matter which one you do. So I'm plugging g into f, and when I plug g into f, remember this whole expression is going in just for that x. That's why I got the square root of x minus 2 squared. Well, those negative 2's are common factors, or they're like terms, excuse me. So that gives me the square root of x minus 4 quantity squared. And if I think about that, what is something squared? Well, it's the square root of x minus 4 times the square root of x minus 4. Well, first times first. Square root of x times the square root of x is x. First times that gives me negative 4. Square root of x. Negative 4 minus 4. Square root of x. Negative 4 times negative 4 is plus 16. These are like terms, so I really actually get x minus 8 square roots of x plus 16, and that is not just x. Therefore, those are not inverses of each other. They are not inverse functions of each other. Okay? And we're going to go to number 4. Well, number 4, I got to find f of g of x. So what I'm doing is I'm setting it out here. Obviously, you can kind of see what I got here when I got the first one done. Okay, I'm plugging g into f. And what I'm seeing here is going on first is these 5's reduce out, so I'm really taking the square root of x squared, which is just x. Well, when I plug f into g now, because remember, this one time is not enough. I need both of these composition functions. That one and that one both have to just equal x. One is not enough. It's got to be both. So I'm going to plug f into g. Well, notice, when I square a square root, that square gets rid of the square root. So I really have 5 times 1 over 5. And remember, that's a 5 over a 1. And we can simplify before we multiply. And we get just an x on that one. Therefore, yes. Okay? Therefore, yes, these are inverse functions of each other. Okay? So that's what you're going to have to do, one or two of those in your homework. Last problem here is an application problem. Okay? The time it takes for one complete swing of a pendulum depends on the length of the pendulum and the acceleration due to gravity. The formula for the time it takes a pendulum to complete one swing is t, okay, where t is the time in seconds, and L, the length of the pendulum in meters, and g is the acceleration due to gravity. Okay, so I'm taking my time. The time it takes for one swing equals 2 pi times the square root of the length of the pendulum divided by acceleration due to gravity. Well, we know, sooner or later you'll have physics, acceleration due to gravity on Earth in meters is 9.8 meters per second squared. Okay? Well, write a function, t of L, okay, time in terms of length of pendulum, that represents the time of one pendulum swing. Well, that is going to be my time in terms of the length of the pendulum is going to equal 2 pi times the square root of the length of the pendulum divided by 9.8, because 9.8 is my acceleration due to gravity. So that is my time in terms of the length of the pendulum for one full swing. Well, now they're going to say, okay, well, what is the graph of this going to be? Oh, Chrome, it's not going to work for me. So I am gonna just come along and we're going to graph this because they want me to find domain, range, x-intercept, y-intercept, and this is not going to be an easy one for us to graph. So I'm going to hit pause so I can move my equation down a little bit here. Okay, so the first thing I want to do is I want to find my domain. Remember, from the warm-up problem, we are only concerned with what is going to make underneath the square root negative. We don't care about the 2 pi. So if L is a negative number, I'm going to have a negative number underneath there. So L needs to be greater than or equal to 0 to keep what's underneath that square root positive, or 0, so I can take the square root. Well, my range in this case is going to be t, all right? When I plug this 0 in here, 0 divided by 9.8 is 0. The square root of 0 is 0 times 2 pi is 0, okay? And then now I just need to know that's kind of like my starting point of my graph, or my range, I should say. So now I'm just going to pick another number in there, like maybe I pick 9.8, because 9.8 is greater than 0. And if I put 9.8 in for L, I'm going to get 9.8 over 9.8. That's going to give me 1. The square root of 1 is 1 times 2 pi is 2 pi, and 2 pi is greater than or equal to 0, so that's my range. Well, what's the x-intercept? Well, the x-intercept, if my domain and range are both starting at 0 and 0, it's going to be 0, 0, obviously, I hope. And the y-intercept is if I put 0 in for x, what is it going to output for y? Well, but not a y, but it's an L-intercept, really, or a t-intercept, I should say, but that's going to give me 0 as 0 as well. Well, if I want to graph this function, I can graph this function, and I apologize for how crummy your graph looks like on your note sheet there. But what we're going to do is I'm just going to make a table of values, and I'm going to be plugging these numbers into that equation using my calculator to graph this. Okay, there's really not a great way to graph this. So I'm thinking of my length of the pendulum, which is my x-axis, and the time it takes in seconds is my y-axis. It's going to be going across there. So I'm thinking 0, put in a 0, I get out a 0. So I'm going to make my point 0, 0. Well, if I put a 1 in for L, and I do the math, I really get 2.007. So I'm getting just a hint over 2. If I put a 3 in there, because I'm using my calculator, I'm going to get 2.838. And again, I'm just plugging 3 into the function we had above there. And that's going to get me a little bit over 3, or just about to 3, I should say. Somewhere in there. I'm going to put a 4 in there even, just to see what's going on. Wait, I skipped 2. Hold on, Carter. Hold on. Skip 2. There you go. So once I made my table of values here, all I did was I took all 5 of these points here and I plotted them on my graph. And now because I know it's a square root function, I know it's going to look like a hook of some sort. Okay? So I'm just going to connect these dots as best I can and say, hey, that's what my pendulum looks like. That's what the graph looks like for that bugger. Well, this one, how long does it take for one complete swing when the length of the pendulum is 0.5 meters? Well, that's saying what time when the length is 0.5 is going to equal 2 pi times the square root of 0.5 divided by 9.8. Yes, I cannot do that with my calculator, but when I type it in, it's going to be approximately 1.24 seconds. So what does that mean? Well, it means if the length of a pendulum is a half a meter long, it's going to take it approximately 1.42 seconds to make an entire swing. Okay? And at one complete swing, it's left and right. Typical grandfather clock pendulum completes one swing in 2 seconds. Okay, so we know we're going to be in 2 seconds. Well, use the graph to determine the approximate length of the pendulum in a typical grandfather clock. So what I'm going to do is I'm simply going to come to my y-axis for seconds, and I'm going to go to 2 seconds, and I'm going to say, right about there, it looks like that is roughly 1 meter. So that would roughly be approximately 1 meter in length for the pendulum. All right? And now the very last one is they say rewrite, all right? Try rewriting T of L as L of T. Well, don't overcomplicate this. This is time equals 2 pi times the square root of, what do we have? We have the length divided by 9.8. What we want to do is we don't need to switch x and y. They're not saying find an inverse. They are saying rewrite the function as L in terms of t. This is t in terms of L. So I'm going to solve this equation for L is all I'm going to do. First thing I'm going to do is I'm going to say t. I'm going to divide both sides by 2 pi. That's going to equal the square root of L over 9.8, right? Hope you guys agree on that. Next thing I got to do is I'm going to have to square to get rid of my square root. So I'm going to have to square both sides. This gets rid of that. That's going to give me L over 9.8. And that is actually going to equal, well, that's going to give me t squared over 2 squared, or 4 pi squared. I got to square everything there. The last thing I'm going to do is I'm going to multiply by 9.8 on both sides. So I can see the 9.8 goes away. So L actually equals 9.8 times time squared divided by 4 pi squared. And what that means is my length in terms of time is going to equal 9.8 times t squared divided by 4 pi squared. And all we did was rewrite that. Notice that we've been finding inverse functions, I understand, but this did not say find the inverse. It said rewrite the function. T is L and L is T. That just means solve your original function for L, move everything over, and then L is in terms of time, because here I plug a time in to get a length, and up here I plug a length in to get a time. And all we did was manipulate our equation. Well, hopefully that made sense to you, and all you got to do is your 13.3 homework, and we will be back tomorrow. Have a great rest of your day.